Hello, AAT. We are in section 2.7, inverse of functions. A function and its inverse can be described as the do and undo functions. So for instance, if you have a simple function like f of x equals x plus 2, its inverse, which is denoted with a little -1 that looks like an exponent, but it's not actually the exponent. It just means the inverse of x is going to be the opposite. So instead of adding 2, you're subtracting 2. So you're undoing what has been done to x in the previous one. If functions f and g are inverses, then if you plug in one for the other, you're going to end up with x if you do that composition of functions, which we talked about in the last section. So for instance, if I plug this in for x there, I'm going to get x minus 2 plus 2, which is of course x. So whenever I have a composition of inverse functions, you're going to end up with x. To find the inverse of a function, we switch the x and y coordinates. A function is called one-to-one if the inverse is also a function. So remember, we talked about how a function always passes the vertical line test. So if you have something like a parabola, it passes the vertical line test. Well, the inverse of a parabola would be a sideways parabola, and it would not pass the vertical line test. So you can tell a function's inverse is a function if it passes the vertical line test and the horizontal line test. Because if it doesn't pass the horizontal line test, meaning it crosses 2 points when you put a horizontal line test through it, then that means once you turned it sideways, it would not have passed the vertical line test. So the inverse would not be the function. And we'll look at some more like that. The inverse is denoted as f to the -1, but it's not actually an exponent. That means the inverse of f of x. There are basically two methods to finding the inverse. If your function is a list of ordered pairs, all you do is switch the x and y. So whatever the domain of one of them is, it's the range of the other. So you're going to switch that domain and range all the x and y values to get the inverse. If your function is shown graphically, you can do the same thing. This is the same thing as reflecting it across the line y equals x. Okay, so here's the easy kind. If you have a function f of x, find the inverse relation, and is that a function? So the inverse, we'll write it as this inverse notation of this ordered pair, is just to switch all the coordinates. So now we got 4, 3. We've got -2, 1. Just switching those x and y's. -1, 5, and 2, 0. Now let's look at this one. Is this a function? If it's a function, you should not see any x's repeated. For every x value, there's only one y value. So yes, this is a function. But is this a function? Well, 4, 3, -2, 1, -1, 5, 2, 0. Yes, no x value is repeated. So yes, it is a function. Okay, so determine the inverse of the function when you're giving ordered pairs listed at a table. So again, your inverse would be to switch all those x and y's. When you write little curly brackets here, it just means each point that's listed. So instead of 1, 2, we have the point 2, 1, 0, -2, switching my x and y's, 3, -1, -1, 0, 1, 2, -2, 3, and 5, 4, and 1, -3. Now this was a function that tells you it was, so is the inverse a function? Well, look and see, are any of those x values repeated? Well, when I look, I say, well, actually, yes. Right here and right here, I have the same x value with 2 different y values. So this is not a function. This inverse is not a function, which means this is not one-to-one. This one is one-to-one. One-to-one means the original is a function and the new one is a function. Okay, so if you have a graph, on the graph below, determine the inverse of the function as shown. So a couple ways you could do it. I could get a couple points. I think that might be the easiest way on this line. So like my original line has the point 0, 3. It has the point, and make sure you're getting points that you can tell, not those fractional points. This point right here is -1, 1. I could get another one, but really all I need is 2 points to determine a line. So if I switch those, the new function would be 3, 0, and 1, -1. So 1, 2, 3, 0, and 1, -1 would be there. Now, when you draw that line, I don't have a ruler with me. You should always use a ruler for your lines, but when I draw it, a function and its inverse should always be reflected through the line y equals x. This is the line y equals x. Goes through 0, 0, has a slope of 1. And so notice, these look like I've just kind of folded the paper over that line y equals x. The point 0, 3 became 3, 0. The point -1, 1 became 1, -1. Okay, so let's look at this. Is this one-to-one? Yes, the original function was a line and the second one was a line. They're both functions. So this is one-to-one. The original graph passed the vertical line and the horizontal line test. Now I already know this one's not going to be one-to-one because even though it passes the vertical line test, it doesn't pass the horizontal line test. So that means once I find the inverse, it's not going to be a function. So it's not one-to-one because it does not pass the horizontal line test. So let's look, let's graph it. So here we'll just take a couple points we know on the original. We've got 0, 0 is a point, 1, 1 is a point, -1, 1 is a point, and let me get one more. I can do 2, 4 is a point. This is that a value of 1. So now I'm going to switch all of those for my new function. So 0, 0, if I switch it, I'm still at 0, 0. If I switch around 1 to 1, I'm still 1 and 1, 1.1, 1, comma 1. If I switch this one, x is 1, y is -1. And if I switch the last one, x is 4, y is 2. 1, 2, 3, 4, 1, 2. You might want to write them out so you're really careful. So this parabola that went up, the new parabola, should go sideways. Woo. All right, so again, notice if I graph that line, y equals x, slope of 1, going through the point 0, 0, it should look like it was folded over and over. And I can double check this graph, this new graph, the inverse is not a function because it doesn't pass a vertical line test. So it's true that it was not one-to-one. The original was not one-to-one. Okay, so solving algebraically. So to solve algebraically for an inverse, all you have to do is make sure that the function is set equal to y, or f of x, swap x and y, and then find a new equation by solving for y. So easy. So we're going to start writing this as y equals, and the inverse is to switch x and y. So because inverse switches the x and y coordinates, and now we just solve for y. So I add 4 to both sides, and I get x plus 4 equals y. And to make it pretty, we'll put it on the other side. Easy, that makes sense. If I undo x minus 4, then my new inverse would be y equals x plus 4. Okay, so we're going to verify that these equations are inverses by using a composition of functions. So composition means I'm going to take the original function and I'm going to plug in the inverse That should be an x, sorry. And see if I come out with x. So the original function was x minus 4. And I'm plugging in for x, x plus 4. So I'm plugging in for x, x plus 4, where x was, and then minus 4. So this was my original x, plugging in x plus 4, the new inverse. And of course, if I simplify that, I will get x. So it is definitely, those are inverses. Okay, this one's the tricky kind. We make sure it equals y. We switch our x and y, and you got to make sure you're switching all of them. So this had 2 x's, so now it's going to have 2 y's. And now I need to solve for y, which is hard because you have two y's there. So I'm going to multiply y up first to the other side. Put a little star. This is a tricky one. X times y equals y plus 1. Whenever you have 2 variables you need to solve for, think about what you're doing. You're solving for y. You need to get those y values to the same side. So I'm going to subtract this y over xy minus y equals 1. Okay, still confusing as to what to do, but I got to get 1 y, so I am going to factor on this next step. I'm going to factor out the y, that's the GCF, and I have y times x minus 1. Y times x is xy, y times 1 is y, equals 1. I want to get y alone, remember what I'm trying to do. So I'm going to divide both sides by xy. Y equals 1, divide both sides by x minus 1. So this is the inverse as soon as it's solved for y. So now I'm going to check with the composition of the functions. I'm going to take the first function and I'm going to plug in the inverse where x was, everywhere x was. So again, this one's tricky. So this was my original function right here. So where x was, I'm going to plug in the inverse. So I have 1 over x minus 1 is where x was, plus 1 over 1 over x minus 1. Ooh, and this is supposed to come out to be just plain x. So to simplify these complex fractions here, fractions and fractions, why not multiply the top and the bottom by that icky denominator, x minus 1. I can multiply the top and the bottom by the same thing because I'm just multiplying by 1, which is perfectly okay. So if I multiply the top by x minus 1, I'm going to get 1 because that cancels, plus x minus 1. And if I multiply the bottom times x minus 1, those cancels, and I just have 1. Okay, then simplify. 1 minus 1 is, of course, 0. And I just end up with x. So I should just end up with x when I'm checking with that composition. That's the hard kind. Okay, number 5. Given the inverse, we want to find the original. Okay, so same thing. Now I'm given the inverse, so I still have my original y is negative 1/2 x plus 1. So to get back to the original, I just need to switch x and y again and solve for y. So I'm going to subtract 1 from both sides. X minus 1 equals negative 1/2 y. I'm trying to solve for y. So to get that fraction to the other side, I can either multiply everything by negative 2, or I can flip it to the other side. I want to get rid of that 1/2, so I'm going to multiply by 2, and I'm going to multiply by negative because I want it to be positive. So I get negative 2x plus 2. Negative 2 times negative 1/2 is just y. So that is my original negative 2x plus 2. And we really should write it in function notation since we were given it as function notation at the beginning. So again, if I plugged in that negative 1/2 x plus 1 into this original, I would end up with x. Okay, then the last one. Determine the inverse of this function. So we have y equals x squared plus 1. So we're going to switch the x and y again. This one's commonly missed because, so we subtract 1, x minus 1 equals y squared. How do I get rid of a square? I square root both sides. And something everybody in AAT always forgets, when you square root both sides, you've got to remember that plus or minus. Don't forget the plus or minus when you're square rooting both sides. So y is equal to positive and negative square root of x minus 1. Don't forget that plus or minus. All right, great job. Make sure you copy